Okay, so in this video, we will talk about vector addition and scalar multiplication. So first, let's talk about vector addition. So mathematically, if I wanted to add two different vectors together to obtain a new vector, basically what we would make sense is to add the components together. So if you wanted to add like 1 comma 3 and add another vector like 2 comma 3, oh God, 2 comma 3, then basically the resulting vector would just be 1 plus 2, which is 3, and then 3 plus 3, which is 6. So it kind of makes sense for us to just add two vectors. That's basically what it is. Now, geometrically, it's a little bit trickier. So basically, what you're doing is that if we place two vectors tail to head, the resultant vector at the tail of the first goes to the head of the second. So this is basically how you do it. So if you have, it really depends on how you're forming it. So let's say this is vector u, and here is vector v. So here's vector v. So this guy is going to actually be the resulting vector. Okay, this is going to be u plus v. Okay, so if you place two vectors where both ends meet, the resulting vector will start where the tails meet as shown. So basically, this is what we kind of call the parallelogram law. So basically what you're doing is that here's vector u and here's vector v, u and v. Well, we can actually have, remember that we can grab vectors and place them in different positions. So I can actually grab this v vector and make it over here. So this is v. And I can actually grab this u vector and make it over here. This is u. So the resulting vector is going to be this. So right here, u plus v. Okay. And that's only if you kind of play it tail to tip, tail to tip. If you were to have two different vectors at the tail, so if you have a vector going this way and a vector going that way, in that case, the resulting vector is going to go right through the middle. Okay, this is u, this is v, u plus v. So this is vector u, this can also be vector v. You can kind of see that it's basically the same exact thing. But if you make it right at the tails, that's what it's going to look like. And I'll give you guys a little bit of an example when we start graphing a couple of the additions in the next one. So vector subtraction works the same way. So one way to kind of think about it is that you can always just change the direction of the vector. So if you have u and then if you have v, then remember, if I change the direction of the vector, this is going to be negative v. Okay, so if I move it to the opposite, then you just have the negative sign of it. And that kind of makes sense, right? You're just kind of alternating the subtractions when you make the vector of the points. So doing so, you can kind of see that vector subtraction is basically the same thing as vector addition. You just have negative components. So, okay, so let's do a couple of problems. So given the following two vectors, u equals 3 comma 2 and v equals 4 comma 5, find u plus v and graph uv and u plus v. So we know that u and v are given, so u plus v is going to be equal to 3 comma 2 plus 4 comma 5. So 3 and 4 is going to give me 7, and then 2 and 5 is also going to give me 7. Okay, so this is going to be u plus v. So if I were to graph this, okay, in the xy plane, so here's x and y. Let's graph vector u first. So I'm going to graph vector u with green. So vector u is going to be 3, 1, 2, 3, and then 2, 1, 2. Okay, so this is going to be vector u. Okay, so this is vector u. Now what I'm going to do is I'm going to graph in purple vector v. So vector v is 4, 1, 2, 3, 4. And then at 5, 1, 2, 3, 4, 5. Okay, so this guy right here is going to be my vector v. Okay, So now what I'm going to do is I'm going to label in red the resulting vector, which is 7, 7. 1, 2, 3, 4, 5, 6, 7, and 5, 6, 7. So basically this guy is going to be right here. So if I graph it, you can see that the vector goes right through the middle of these two. So, and this kind of makes sense because in kind of like how we were looking at the parallelogram, you can make a parallelogram by moving this vector u up here. So notice that this guy is still vector u. Okay, if I were to make it like that, and then if I were to have the v vector go from this tail to this tail, notice that this is still vector v. So you can kind of see this parallelogram, and then the diagonal is going to be the sum of the two vectors. Okay, so geometrically, this is kind of what's going on. So this is going to be u plus v, so the sum of the two vectors. So imagine that you have two different forces pointing that way, and the sum of the two forces is going through here, okay, right through the middle. Okay, so just a really FYI, kind of like how you, just giving you a little bit of an idea of how these vectors are working. So when you think about scalar multiplication, so we're going to talk about scalar multiplication, not vector multiplication. So we're basically taking a number and multiplying it by the vector. So you're taking k, which is a real number, and multiplying it by a vector. And basically what you're doing, you're either enlarging the vector, so making it bigger, shortening the vector, or switching its directions. Okay? So, and that makes sense, right? Because if you have 3, 2, and if I multiply this by a -2, then not only am I switching the direction of it, so now this is going in the opposite direction, but I'm also doubling it in size. So this is going to be a 6, and now this is going to be a 4. So I doubled it in size, and I swapped the direction of the vector. Okay, so here I basically tell you that if you want to multiply the vector by a scalar, like any number, then you just multiply each of the components. So here, let's do this example. So given these two vectors, let's add them together first. So I want to do u plus v. So that's going to be -3, 4. Plus 0, 8. Okay, so we're going to add the components together. That's going to give me -3, and this is going to give me just a 12. Okay, so you can kind of imagine that if I draw these two vectors, this new resulting vector, which is called the resultant vector, is going to go right through the middle. Okay. All right, so now let's do the next problem. So now we're multiplying each of the vectors by a scalar multiple. So 3 times v, so v in this case is 0, 8, minus a 7, so I'm making it 7 times as large, this -3, 4. Okay, so this is going to give me, so the first one is going to just be 0, making a 3 times as big, that's going to give me 24. And then minus this 7 and this 3 is going to give me a -21. And this 7 and this 4 is going to give me a 28. Okay, and then I'm going to leave the negative there. So I have 0 minus a -21. That's going to give me a +21. Then this 24 minus this 28 is going to give me a -4. Okay, so basically what I did is I made v 3 times as large, u 7 times as large, subtracted the two vectors, and I got this new vector. Okay. This other one says -3/4 u. So I'm basically multiplying this vector by 75%, and then switching it around. So -3/4 u. So u in this case is going to be -3/4. So you're going to have +9 over 4, and then comma -3. Okay, so this is going to be my new vector when I multiply it by 0.75. Okay, so now we want to find the absolute value of u, so which is basically the magnitude, and find the direction of vector v. Okay, so let's find the magnitude of u. So remember, u was just equal to -3, 4. So that's going to be -3 squared plus 4 squared. That's going to give me 9 plus 16. Which is going to give me the square root of 25, which is 5. So the length of this vector is just going to be 5. The then the direction of v, so that's going to be theta is equal to inverse tangent of v. So v in this case was 0, 8, so we're going to do 8, 0, 8 over 0. Okay, so that's going to give me undefined. So we got to think about where's tangent undefined. That's at pi over 2, which is basically at 90 degrees. Okay, and that makes sense because if you look at the vector 0, 8, you see that there's no x value going in the x direction, and in the y direction you're going up 8 units. So the vector is just pointing up in the north direction, if you want to think about it, north. Okay. All right, so you have those types of vectors. So now something else that you can do with these vectors is something called finding the unit vector. Okay, so finding the unit vector, actually what it does is that you're making the vector into a magnitude of 1. Okay, so sometimes using unit vectors are useful in simplifying calculations. So the way that you do it is that you take the vector v and divide it by the magnitude. Okay, so let's just find the unit vector of this guy. So what you're going to do now to find this unit vector u is you're going to take this guy and then divide it by the magnitude of -3, -7. Okay? So you're going to have a -3, -7 divided by the magnitude of this guy, which is the square root of -3 squared plus -7 squared. Okay? So you're going to have -3, -7. All right, so what is that one going to give me? So you're going to take, that's going to be 9 plus 49. That's going to give me 58. So if I take the square root of 58 on the bottom. So now all I'm going to do, imagine this is a scalar. I'm just going to divide it by both of these guys. So my unit vector is going to be -3 divided by square root of 58. Comma, -7 divided by square root of 58. So that's going to be my unit vector. Okay, so and the way to check your work to make sure that it actually has a magnitude of 1, take the magnitude of u. Okay, so it will be the square root of -3 over square root of 58 squared, and then take -7 over the square root of 58 squared, and to check, and this actually is going to give me 1. So working with these vectors actually works a lot in your favor, especially when we're talking about normal vectors. And this will be more in Calc 3. But just a little glimpse of what exactly these vectors are doing. So just to kind of give you one last thing, here is what we call performing operations with vectors in terms of I and j. So sometimes we have two different types of ways to talk about vectors. We have it in component form, and we also have ij form. Okay, so I use both different types of forms, and in physics you will use that. So don't confuse the I for the imaginary number. So basically I here is basically the vector 1, 0. And j here is the standard vector 0, 1. So if you think about that, the 1, 0 is going in this direction, so it's a unit vector. And the j vector is going in the y direction, and it's only one, a magnitude of 1, so it's also a unit vector. So this is your I, and this is your j. Okay? So basically, we can write any type of a vector just with the I and j. So instead of, we drop the components, and instead we just write an I for the x values and a j for the y values. Okay? So let's do this example. So suppose that you have these two different points. So write them in terms of I and j. So first, let's try to figure out what this should be. So we're going to subtract the x values. Okay, so it's going to be -2 minus 3. And you're going to write I. And then you're going to take this -12 minus -10. And we're going to write j. So this is going to give me -5i. This is gonna be positive, so that's gonna give me what? -2j. So this is how we write the vector. Okay. Sometimes you can write a hat, so I hat, where there's like a little pointy little arrow. So sometimes you tend to see this often. Either works. You can write just regular I or regular J. So this is what we call IJ form. Okay, so if you want the vector in IJ form, this is how you want to write it. You can always write it in component form as well. But typically, if something starts off in IJ form, then you want to end it in IJ form. If it starts in component form, you want to end it in component form. Okay, if it's a mix of both of them, then you can just choose whichever you want. Okay, so so you can find also the components of a vector x and y when you are given the magnitude and the direction of the vector. So if you're just given the magnitude and direction, you can actually find the components. Okay, so if I don't know what these components are, or if I were doing I and j, then if I don't know what these guys are, but I know what their magnitude and direction are, then I can just do it. So it's just x is equal to the magnitude of v cosine theta, y is equal to the magnitude of v sine theta. So this kind of looks very familiar, right? Because this is basically the polar formulas. Okay, just instead, we just replace the r with the magnitude because r is just the magnitude. So let's do this. So find the vector. Find the vector with length 13 and angle 225 to the positive x-axis in IJ form. So we want it in this form, not in this form. Okay, so all we got to do is figure out what the component, like what x is. So x is going to be the magnitude, which is going to be 13 cosine of 225. And then we're going to find the y component, which is going to be 13 that's going to be sine. Sine of 225. Okay, so we're going to take the cosine of 225 degrees. That's going to give me negative square root of 2 over 2. Which gives me negative 13 square root of 2 over 2. And then you're going to take the sine of 225 degrees. And that's going to give me also negative square root of 2 over 2. Okay, so negative 13 square root of 2 over 2. Now you don't want to finish there. Remember, you wanted an IJ form. So you're going to have negative 13 square root of 2 over 2 I plus, oh, no, it should be minus 13 square root of 2 over 2 J. So this would be the vector that has magnitude 13 and it has an angle of 225 degrees. So if I were to draw it, notice that this is negative and then the other one's negative. So if I were to draw the standard, it would go there. Angle here would be 225. The length of this vector will be 13.